All right, this is a nice model of harmonic oscillations, driven harmonic oscillations. If you're in a mechanics class, that's a pretty important topic that you have to cover. In Physics 240, this makes a nice model for a resonant LRC-driven oscillator, in which case this mass represents the inductance and the spring represents the capacitance. In any case, I'd like to point out that this mass spring system has a natural frequency, which you can tell by just displacing a little bit and watching it wobble. That's the natural frequency of this system. We drive the system through this string that is connected to a wiffle ball up here. It is connected to a system of pulleys to a generator. The string is connected off center cam, to the generator. You can see that as we rotate the generator, we pull on the string, and that creates a pull on the wiffle ball, and that will cause forces to expand and contract the spring, and that will be transmitted to the ball. Okay, so I'm going to go ahead and turn the system on and slowly turn up the voltage. One analogy I like to use about what's happening here, it does not appear to be on.
It wasn't. You might have turned it off.
It was on and I turned it off. Okay, so one analogy I like to use for what's happening here is that as we change the frequency, we're changing the rate at which you're pulsing this wiffle ball. Imagine you take a younger sibling to the park and they get on the swing set, and you close your eyes and you push them on the swing set. Some of the time you push them in the direction they're going, some of the times you push them the opposite direction. You're basically not going to add very much energy that way. If you always push them when they're moving away from you, however, you will put a lot of energy into the system and the swing set will go very high. So here we go. Low frequency, you can see that the ball isn't really moving all that much. I'm going to continue to increase the frequency. By the way, I could have mentioned this before, but there's a little bit of friction added to the system where the string is going through the post there. So we're getting close. You'll notice that it starts getting larger oscillations, and then it dies off. We're not quite at the resonant frequency, but we're at a frequency where we're pushing the same direction for a while, and then we're pushing the other direction as they go in and out of phase with each other. When we drive it at exactly the frequency it wants to go, we get really large oscillations. I might be able to do a little better than that, although it's pretty close to the resonant frequency right now. No, I just went past it. Notice that when you go past the resonant frequency, you go in and out of phase again, and I'm going to continue turning up the frequency. Notice that this is turning really rapidly, and we're getting almost nothing in this ball, whereas the wiffle ball is oscillating quite rapidly. Basically, this is the case where you're pushing it the opposite of the direction it wants to go half the time. So we're adding energy in, and then we're subtracting it right back out again, and the ball just doesn't go anywhere. I'm going to lower it down to see if I can hit that resonant frequency again. You get a really large response from the ball when you drive it at the frequency it wants to go, because at that frequency, every time you push on the ball, it's going the direction you're pushing. Every time you pull on the ball, it's going the direction you're pulling, and you just always add energy to the system.